everyone, my name is AJ, and today I'll be introducing the topic of proof by induction. Proof by induction is a very powerful proof technique that can be used to prove propositions of a certain form. Before going over proof by induction, however, I'd like to review a few of the proof techniques that we already know so we can have a better context of where proof by induction fits in. So what are some proof techniques that we already know? Before even getting into that, what's our goal? Our goal generally is to prove statements of this form. P implies Q, where P and Q are both propositions. Propositions can be either true or false, and this is the conditional statement, which basically states that if P is true, then Q is true. Okay. So given that our goal is to prove the statement P implies Q, what techniques do we already have? What proof techniques do we already know that can help us assert this? Well, one proof technique that we already know is a direct proof. The direct proof involves us assuming that the statement is P is true, and then given that P is true, when we assume that, we reason directly to prove that Q is true, hence the same direct proof. Another proof technique that we already know is proof by contrapositive. Proof by contrapositive is based on the fact that any conditional statement, such as P implies Q, is equivalent to the statement not Q implies P, logically. Not P, sorry. If we can prove that not Q implies not P, then we've automatically proved that P implies Q, because they are both logically equivalent. Another proof technique that you're probably familiar with is proof by contradiction. Proof by contradiction, as you may already know, we assume, in order to prove a statement such as this, with contradiction, we first assume that P is true, then we assume that Q is not true. In other words, we assume that not Q is true. Then, we directly reason about in some way, and then we reach some kind of contradiction. Usually that contradiction might be, we find out that not P is true. But this contradicts the fact that we assumed that P was true. And this allows us to conclude that Q is true. So that's proof by contradiction, a technique we often see in many of the problems we solve. So the fourth technique, which I'm showing you today, is proof by induction. Alrighty, so what exactly is proof by induction? Well, you might not have realized it, but you've actually already used proof by induction to prove many of the things that you see in your daily life. So when we were kids, some of us might have played with dominoes. You might have seen YouTube videos online where people knock down some kind of domino, and then there's this huge fancy chain of dominoes falling all over, and it's very exciting. So if I asked you to prove to me that if I knocked out the first domino, that the last domino will be knocked out, what would you say? You'd probably call me crazy and be like, of course it's obvious. If you knock out the first domino, all of them will be knocked down. It's physics. Well, formally, to prove this, we know that we knock down the first domino by touching it. Then given that an arbitrary domino is knocked down, we take for granted the fact that if that domino is knocked down, then it will automatically physically knock down the second domino right after it. So there's that basis step where we assume we knocked out the first domino. Then there's this kind of inductive reasoning step where we know that if an arbitrary domino is knocked down, then the domino right after it will also be knocked down. Thus, with those two steps, this basis step, as well as this inductive step, we've proved that the last domino has been knocked down as well as a result. Where else have we seen proof by induction? Flights of stairs. So we take stairs for granted. We know that if we go up some stairs, then we'll be able to reach the last step. How do you know this, though? You know that you can get to the first step. You just walk over there, and then you're there. And then, given that that's like a basis step, then we also know that if we're on an arbitrary step, we should be able to step up, there's some kind of normal force that when we push ourselves up from the ground, we were able to escalate to this step right above that. So basis step, we can reach literally to the first step. Then there's an inductive step. If we're on an arbitrary step, then we should be able to step up and get to the step after it. So by that reasoning, we can get to the first step. Then that implies we can get to the step after that, which implies we can get up to the step right after that. Keep going, and finally we've reached the top. So that's the basic intuition of proof by induction. You already know what it is, now we just have to apply it to math. So how exactly do we use proof by induction to prove mathematical assertions? First off, what kind of assertions is proof by induction best suited for? Proof by induction is best suited for assertions of this form. For all n, prove that P of n is true, where n is greater than or equal to some b. Okay, so let me give you an example of a statement that it could be of this form. You've probably seen this summation formula before, probably in high school classes or even your early college classes. Summation from I equals 1 to n of I is equal to n over 2 times n plus 1. So if we actually expand this out, this is basically asserting that if you take the sum of the numbers from 1 all the way to n, then you will get n over 2 times n plus 1. Okay, so people have told you that this is a formula that's true. How do we know it's true? How do we prove it? This is a very valid candidate for proof by induction. So, given that proof by induction consists of a basis step and an inductive step, we can reason about to proving the statement. A basis step is like the initial step here, where we either step up the staircase, take that first step, or we want to knock down the first domino. So, we have a propositional function p, and this is a variable inside it n. So the basis step involves that we have to prove that p of b is true. Remember I was saying that this is the form? We want to prove the statement for all n greater than or equal to b. So b is like the initial step. So what's p of b in this example? Given the proposition here, we can say that P of n in this case is this summation. This is my proposition, and I want to prove it. And now, the basis step is I want to prove P of b. Let's say that we want to prove this is true for all n greater than or equal to 1. B in this case would be 1. So the basis step, P of 1, we want to prove that the sum of I equals 1 to 1 of I is equal to 1 over 2 times 1 plus 1. All I did here was I substituted the variable 1 as n into this propositional function. Wherever there was an n, I put a 1. So I want to prove for the basis step that this is true. Okay, so is this true? This summation on the left, if you just sum all numbers from 1 to 1, you'll just get 1, right? Well, what's this right side equal to? Half times 1 plus 1. That's just half times 2, which is equal to 1. And that's all there is to it. That's the basis step. We proved that P of 1 is true. So that's equivalent to knocking down the first domino. So remember I was mentioning that there's an inductive step. We want to prove that if an arbitrary domino is knocked down, then the one after it will also be knocked down. So what is our inductive step? I'll erase this. What would be our inductive step here? Well, inductive steps in mathematical proofs, they take the form that where we want to prove that P of k implies P of k plus 1. We have to prove that this is true in order to complete our proof by induction. Okay, so how do we prove a conditional statement? To prove a conditional statement, we first assume that this is true. Suppose that P of k is true. In other words, suppose that the summation of I equals 1 to k of I is equal to k over 2 times k plus 1. Assume this is true. Now, we need to prove that k plus 1, the sum from I equals 1 to k plus 1, is equal to k plus 1 over 2 times k plus 1 plus 1. I derived this proposition, we're substituting k plus 1, into our propositional function here. So given that this is true, we want to prove that this is true. So how do we go about this? We know that this is true, and we're trying to prove that this is true. Well, we know that k plus 1, the summation from I equals 1 to k plus 1 of I is equal to the summation from I equals 1 to k plus of I plus k plus 1. Okay? Then we utilize our inductive, this is called our inductive hypothesis, the part that we assume is true, P of k. We can substitute our inductive hypothesis back into this proposition. So we assumed that this was true. This is equal to k over 2 times k plus 1 plus k plus 1. Okay, so we have this. We want to prove this. Somehow we need to show that that is equal to this. It's really just easy algebra. So we know, so just simpling this out further, it does not affect the proof significantly, but this is ultimately what we want. We need to somehow equate this to being equal to that. Well, it seems like we can factor out the k plus 1 from here. this is equal to k plus 1 times half plus 1, or rather k over 2 plus 1. And then notice that we can factor out a half times k plus 2. And voila. We went from our inductive hypothesis, we assumed this was true, and then we proved that p of k plus 1 is true as well. So I had erased it before because I was running out of space. But remember, we had a basis step where we proved that p of 1 was true. We proved that p of 1 was true by showing that the summation from I equals 1 to 1 of I is equal to 1, which is equal to 1 over 2 times 1 plus 1, which equals 1. So this concludes our proof by induction. What exactly just happened? Good question. We proved that p of 1 is true, and then we proved that p of k implies that p of k plus 1 is true. Where does this lead us? If we know that p of 1 is true, that means that p of 2 is true. And if p of 2 is true, then p of 3 is true. And so on. P of 3 implies p of 4. And thus, we have proved our original proposition. For all n is greater than or equal to 1, the summation from I equals 1 to n of I is equal to n over 2 times n plus 1. So it's just like walking up a ladder. I erased the picture. Walking up a ladder and knocking down dominoes, but that's the idea. You have a basis step that you prove is true. Then you have an inductive step where you assume the proposition is true for an arbitrary k. And then you prove that the proposition is true for k plus 1. So there are many more examples where we can use proof by induction, and there are a lot of beautiful proofs that use this to derive many certain facts about mathematics. That concludes my video. Thank you for listening.